Section 1.8, Logarithmic Functions. So I mentioned in the previous section on exponential functions that we do have inverses for these functions. This is possible because any exponential function f of x equals b to the x is going to be 1 to 1. Logarithmic functions are defined as inverses to exponential functions. Thus, y is equal to log base b of x if and only if b to the y is equal to x, like that. So the base is equal to b. Notice that the base in the logarithmic form appears down here underneath, kind of subscript to the word log. And then x, what used to be the input for our logarithmic function, is the output for the exponential. Okay, and then this y, so y is like the input to the exponential function, becomes the output to the logarithmic function. So notice that we define this log function in such a way that we take the exponential function, we just switch the inputs and the outputs. That's exactly what an inverse function does. All right, so this is a little bit strange and it takes a little bit of getting used to, but we're going to see a bunch of examples and we'll get a little more comfortable with these logarithmic functions. First, I want to look at some common types of logarithmic functions. So the first one is just called the common logarithm, and this is the logarithm base 10. So log base 10 of x, and we actually have a shorthand for this. We just write this log x. So if there's no number written down there subscript to log, we just assume that it's base 10, and we call that the common logarithm. Another very special logarithmic function is the natural logarithm, where the base is that number e. Remember, e is Euler's number, and it's approximately 2.718 something something something. So the natural logarithm is log base e, and we just write that ln of x. Usually when I write it by hand, I'll do it kind of like in cursive, like natural log of x. So like we mentioned in the last section, e is a very special number. We have buttons on the calculator which are reserved for the exponential function e to the x, and also the logarithmic function, the natural log of x. So you'll see a button on your calculator which actually has ln of x on it. And that's what that means. Okay, so we'll deal with both of those functions a little bit later. Let's look at some examples, just getting used to the basic machinery of logarithms and how we can work with them. So we want to rewrite log base 3 of 1/3 is equal to -1 in exponential form. So something we'll have to do a lot in this class is like go between logarithmic and exponential form. So remember, since logarithms are inverses to exponential functions, the input to the logarithmic function, or in this case, it's like a logarithmic equation, but the thing that is actually getting plugged into the logarithm is this 1/3. So that will be the output of our exponential equation. So, our exponential form, it's going to be something like b to the y equals x. So the x is what was the input for the logarithmic equation. So that is going to be 1/3. So 1/3 is going to go out here. The -1 over here, this is sort of like, it's looking like the output. It's by itself on one side of the equation. That is going to be the input for the exponential equation. So that -1 is actually going to appear up here in the exponent's place. And kind of the easiest thing is the base. What's the base going to be? Well, the base in the logarithm is going to be the same as the base in the exponential equation. It's just going to be 3. And we can sort of check that we get a true statement here. Is this true, that 3 to the negative first power equals 1/3? Yes, it is, because we're confident with our properties of exponents. We know that if we raise something to a negative power, really we're just looking at the reciprocal of that value. Okay, example 2, we want to go the other direction. So we want to rewrite 9 to the 1/2 is equal to 3. We want to write this in logarithmic form. Okay, so when writing something in logarithmic form, it's going to be log base something. And like I said before, the base is kind of the easy thing because it's the same as the base in the exponential equation. But it's going to be log base b of x is equal to y. Okay, so for this one, the base b is going to be 9. Log base b of x equals y. The way I think of this is b to what power y equals x. Because it's kind of like, remember, the exponent is isolated on one side of the equation when we're looking at it in logarithmic form. So the exponent is going to be by itself over here. Okay, so this y over here is the exponent, and the x is going to be whatever is by itself, like the value that we get by actually raising 9 to that exponent. So this is going to be log base 9 of 3 is equal to 1/2. So that is how we would write this in logarithmic form. So we have to be able to go in both directions. We have to be able to take something that's in logarithmic form and recognize, okay, what's the base, what's the exponent, and we have to be able to look at something in exponential form and recognize what's the base, where does the exponent go in this equation. And that's usually how I think of it. The exponent is going to be isolated by itself on one side of the equation. Okay, looking at a couple of special properties down here. So one thing to remember, since these logarithmic functions came from exponential functions, it's the same base b, so we have those same conditions. Remember, b has to be a real number. So I'll say b is a real number, and b is greater than 0. Okay, and generally b is not equal to 1. Okay, because when b is equal to 1, it's kind of a trivial case. Nothing interesting happens, so we don't use a base of 1 ever. Okay, so if we're looking at log base b of 1, so just thinking through kind of like how I was talking about this expression up here in the last problem, I'm thinking b to what power is equal to 1? So 1 is an interesting one. How can we raise a number to some exponent and get 1 as the output? Well, anything raised to the 0th power is equal to 1. So that's the property we have. Log base b of 1 is always going to be equal to 0. And if you think more clearly in terms of exponents, I think most of us do, rewriting this equation in exponential form, it would be b to the 0th power equals 1. Right? Like I think we all understand this, we remember this. So just rewriting that property in logarithmic form is going to look like that. Okay, how about this next one? Log base b of b. So this is asking like b to what power gives us b? Okay, you could even go to exponential form before we finish evaluating it. It's like b to what power, a little blank space up here, b to what power equals b? Well, 1. If we raise it to the first power, we're going to get the identity, right? So this is just 1. Log base b of b is equal to 1. Okay, this next one is not quite as intuitive, like it's not as easy to figure it out as these ones over here. B to the power of log base b of x. It turns out this is just equal to x. Why is this the case? Well, remember, b to the x and log base b of x are inverses of one another. And what happens if we have two inverses, like if we look at f inverse of f of x? What happens when we compose a function with this inverse? They just act as the identity, and the output is just x. Okay, and this just comes from inverse function properties. Okay, very similar thing happening in this fourth and last special property for logarithms. What if we have log base b of b to the y? This is just going to be equal to y for the same reason, right? This is just composing an exponential function inside of a logarithmic function, and they sort of cancel each other out, and we're just left with the identity. Okay, let's try example 3. So this is just doing some arithmetic, really. With logarithms, let's see if we could figure these out. So for A, we're looking at log base 8 of 8. So I know this looks like we have some it's hard to imagine that this is just going to simplify down to some real number, but it is. What this is asking, like the way that I, again, sort of state this to myself in English, is it's like 8, the base, to what power is equal to 8, the input? Or I could write this in exponential form. It would look like this. 8 to what power is equal to 8? So this is actually one of our special cases, right? This is like special case number 2. Log base b of b is equal to 1. So this is just going to be equal to 1. All right, but I still draw out the exponential form of the equation just because I never memorize these. I don't memorize this kind of stuff. I just try to have a procedure, kind of a mental procedure that I can go through to figure out what this logarithmic expression is equal to. And that procedure is converting it to exponential form. How about this one, log base 19 of 1? Well, the exponential form is like 19 to what power is equal to 1? Well, hey, remember, anything to the 0th power is equal to 1. So this must be equal to 0. Right? So we're really coming up with the exponent. That's what we're looking for. Like the logarithm itself, like when we evaluate a logarithm, really what this simplifies down to is the exponent. So how about this one? 6 to what power gives us 36? Well, 6 squared gives us 36. How about this one? 3 to what power gives us 1/9? So 3 to what power gives us 1/9? Well, a couple things. I see that some type of reciprocal has been taken here, right? Because we're ending up with a fraction, a value that's less than 1. So I think this is going to be a negative value. And in the denominator, we have the second power. Like we have 3 squared, we have 9. So this is going to be -2, right? 3 to the negative second power gives us 1/9. All right, so I feel like with a lot of these, it's just a little puzzle, converting it to exponential form, playing around with it, seeing if you can figure out what the exponent is. How about natural log of e? So we might have to remind ourselves, the natural log, that's just shorthand for log base e of e. This is asking us e to what power equals e. That's just going to be 1. All right, so don't get too scared when things go in terms of, natural logarithms and e to the x. We can still get pretty reasonable, simple answers to these expressions. This next one has a little more to it. For f, we're looking at the natural log of the square root of e. So again, this is log base e. And I won't write this out like this every time. At a certain point, you're just expected to understand that the natural log is log base e. I'm also going to rewrite this e as e to the 1/2 power. Okay, remember we can represent a root, whether it be a square root or a cube root or an nth root, with a rational exponent like this. So putting this in exponential form, really we're saying e to what power is equal to e to the 1/2 power? Well, 1/2. Okay, so this will be my answer for this one. I should box up all these. Logarithms are interesting and challenging because when we're evaluating them, really we are searching for the exponent. Okay, but once you could look at an expression like this and think, okay, e to what power equals the square root of e? Once you just sort of have that sort of basic machinery of the logarithm internalized, you should be able to piece together and evaluate these simple logarithmic expressions. Let's keep moving. How about graphs of logarithmic functions? If you have an original function f of x, in this case, we'll just call that, f of x equals b to the x, the graph of its inverse will look exactly the same, but just reflected over this diagonal line, y equals x. So here is the graph of y equals log base b of x. Okay, and this first picture, really this is if we have a starting function or an exponential function where the base b is greater than 1. So we have this like increasing kind of behavior here. Now, if we have our base b is between 0 and 1, think of that graph of like 1/2 to the x that we did back on page 26, I think. And we have like a decreasing exponential function. The associated logarithmic function will look like this. It'll also be decreasing, but the shape will sort of look like that. So something I want to point out here is, remember, for exponential functions, generally for the parent functions, we have a horizontal asymptote at the x-axis, or the line y equals 0. So for our logarithmic functions, we will have a vertical asymptote at the x-axis, or excuse me, at the y-axis, or the line x equals 0. So let's check out a couple properties here onto page 30. So we're looking at logarithmic functions in the form f of x equals log base b of x. If b is greater than 1, then the function is increasing. If b is between 0 and 1, then the function will be decreasing. All right, and we do not look at values of b which are negative. You'll never see log base b where b is a negative number, because these are defined in terms of our exponential functions, which have that same restriction. Okay, and then x equals 0, that line will be a vertical asymptote like we were just talking about. How about domain and range? So a property that you should recall from your college algebra class is that the domain of a function f is equal to the range of its inverse. And the range of a function f is equal to the domain of its inverse. Okay, so remember the range of an exponential function, or of our sort of like parent exponential function b to the x, is 0 to positive infinity. So that is going to be the domain for the inverse log base b of x. And we could sort of verify that graphically. Like, remember this red line here is the graph of the logarithmic function. And notice, since we have this vertical asymptote at the y-axis, we only have this function defined for values of x that are to the right of that y-axis. So for x values that are greater than, strictly greater than 0. So there's our domain, all values of x from 0 to positive infinity. Now the range is going to be the same as the domain of our exponential function, b to the x. So this will be all real numbers. And again, we can look back to the graph, this red line here, or this red line over here, and we can see that the range, all of the y values that will be covered by this graph, it's going to be all real numbers, negative infinity to positive infinity. We only have that restriction on the domain. No negative values, and 0 can't go in either. Okay, and then we have an x-intercept 1, 0. Sorry, I know I'm bouncing quickly between the graph and these properties here, but remember, for the graphs of exponential functions, if it's in the form y equals b to the x, we're guaranteed that ordered pair 0, 1. So it's like we're guaranteed that y-intercept. For logarithmic functions, if it's in the form y equals log base b of x, we are guaranteed this x-intercept at the ordered pair 1, 0. Okay, so that is what this is all about. And there are no y-intercepts because the y-axis is a vertical asymptote. Logarithmic functions are also continuous on their domain and one-to-one. So let's actually graph one of these. Example 4, we want to graph the function f of x equals log base 2 of x and state its domain and range. So we can make a table of values, plug some input values. And you know what? I'm actually going to do one of these, I call it an H table rather than a T table. This is an H table. So we'll have some input values x, some output values f of x, and in the middle we're just looking at log base 2 of x, just giving myself a little space to work things out here. So I'm going to plug in some values x, and I have to be sort of clever or thoughtful about what values I plug into this function, because log base 2 of x, this is sort of a sensitive function in the sense that, remember y equals the square root of x. There are only certain numbers that are nice to plug into this function. I want to plug in perfect squares. Like if I plug in 1, I get a nice output. If I put in x equals 4, I get a nice output. Or if I put in 9 or 25, right? I want to plug perfect squares into the square root function to get nice whole number outputs. Now for a logarithmic function, because remember, this input value is like 2 raised to some power. So for my input values, I want to use powers of 2. So I can plug in 1, I can plug in 2, I can put in 4, 8. Notice that these are just powers of 2, right? 1 is 2 to the 0th power. This is 2 to the 1st power. This is 2 to the 2nd power, and so on, 2 to the 3rd power. I also might use as an input 1/2 and 1/4. Okay, so to evaluate the function, log base 2 of x, if I put in 1, log base 2 of 1, this is saying 2 to what power gives us 1? Well, 2 to the 0th power gives us 1. How about this? Log base 2 of 2. 2 to what power gives us 2? Well, 2 to the first power gives us 2. Okay, how about, what about log base 2 of 4? So how do I evaluate this? Log base 2 of 4, well, it's asking me 2 to what power gives me 4? 2 squared gives me 4. Okay, and 2 cubed gives me 8. And how about this one? Log base 2 of 1/2. 2 to what power gives me 1/2? Well, this is going to be a negative number because, I have a fraction as an input into this logarithm. So some kind of, like a reciprocal was taken. So it's going to be a negative exponent, and it's just going to be a negative first power. Right? Log base 2 of 1/4 is going to be negative 2, and so on. So by taking this approach here, I get a bunch of ordered pairs, 1, 0, 2, 1, 4, 2, and so on. So let me plot these points. 1, 0, 2, 1, 4, 2. I'll have the ordered pair 8, 3. If I put in 1/2, I got out negative 1. If I put in 1/4, I got out negative 2. And we can sort of see this graph coming together here. There we have it. That is y equals, or let's see, I called it f of x. That's the graph of f right there. And we can see we have that vertical asymptote that we were expecting at the line x equals 0, aka the y-intercept. Okay, so I would recommend that you sort of memorize and internalize logarithmic graphs, at least knowing what y equals log base 2 of x looks like, and, y equals log base 3 of x, like being able to come up with these without doing a table of values would be a good call. Because for problems like example 5, yes, we're graphing a logarithmic function, but we also have a bunch of transformations here. Saying this plus 2, that indicates some kind of horizontal shift. There's a negative sign out in front. That's a reflection. We're shifting vertically as well. So when we're graphing functions that have more going on, like this one here, I'd rather not have to think too hard about getting the graph of the parent function so that I could just sort of focus on the transformations. Because for this one, the parent function, p of x, is just going to be log base 3 of x. So I might quickly just sort of sketch what that looks like. I have this one memorized. So 3, 1 is an ordered pair. We also have 9, 2. Put in 1/3, I get out negative 1. So anyway, parent graph looks something like this. All right, so what are my transformations? I'd like to just focus on transformations so that I don't have to do a table of values at all for this graph. So if I express f in terms of the parent function p, f of x is negative p of x, then we have that plus 2 happening on the inside of the parentheses, and then minus 3. Okay, so I'm just trying to demonstrate here how we can build the graph of f of x off of the graph of our parent function log base 3 of x. Okay, so given what I know about transformations of functions, we've got a couple things going on here. This right here is a reflection over the x-axis. Remember, whenever we have a +2 on the inside of the parent function, this is a horizontal shift, particularly 2 units to the left. So I'll say shift 2 units to the left. And then the -3 is just down. Vertical shift down by 3 units. Okay. The order of transformations does matter. Okay, so the order of transformations, first we want to do the horizontal shift, and then we want to do the reflection, and last we do the vertical shift. Okay, so if you have to remind yourself of, this process, a couple of Googleable terms, or you could also ask me about these in office hours if you want more examples or more demonstration, but this is just transformations of functions. And being mindful of the order of transformations. We actually covered this in the first section, or maybe second section of this first chapter, order of transformations. Very good. Okay, let's do it. I'm going to start by shifting it 2 units to the left. So, okay, my parent function, first let's go 2 units to the left. So I'm just moving each of these points over by 2 units. So I'll have, that kind of graph. Of course, my horizontal asymptote also gets shifted over by 2 units to the left. So I have something like that. I also want to reflect over the x-axis. So that's just going to take every point on this graph and it's just going to flip it to the other side. Okay. Notice I'm just taking every ordered pair, all the blue points that I drew in, and just reflecting them to the other side of the x-axis. That one ordered pair that is on the x-axis doesn't move, right? That one is just fixed. So then we get that. I'm just going to color code, the reflection over the x-axis step. That's the one I did in purple. And the final step is shifting that graph down by 3 units. And I'll just graph this in a solid line in black. So let's shift this down by 3 units. So I'm just taking each of those points, moving them down by 3. Down 1, 2, 3. Okay, so I'm going to erase the mess now. And here is what our final graph should look like. Should look something like that. I'll put a little dotted line here to indicate that I have a vertical asymptote at the line x equals -2, right, as a result of that shift 2 units to the left. And this is my graph. At least I hope it is. How might I check my answer? Sometimes I'll just find an ordered pair on the graph. So that's the ordered pair, let's see, 2, 4, 6, 7. So that's the ordered pair 7, -5. One way that you could sort of check your work is if I plug 7 into my original function, I should get out -5. So This is sort of a check. I'll maybe just do this down here. Check. F of 7. What happens if I evaluate this function at 7? So negative log base 3 of 7 plus 2 minus 3. I'm hoping that this is equal to negative 5. Okay, so I'll put a little question mark over that equal sign because I don't know. Let's see. Negative log base 3 of 9, just PEMDAS, simplifying inside of the parentheses. Okay, log base 3 of 9, I can evaluate that. 3 to the second power is equal to 9, so this is really a negative 2. And what is negative 2 minus 3? It is, in fact, negative 5. Okay, so what I did there is really I was just using this one ordered pair right here. This is not bulletproof. This is not this doesn't completely guarantee that my graph is correct for every single point. But since I was using transformations of functions and shifting around, that gives me a little more confidence that I ended up with the correct graph, just choosing that one point and seeing that it does give me a true statement when plugged into my function. Okay, but this is really our answer here. We just wanted to come up with a graph for f of x, and that's what we did. Example 6, we want to find the domain of f of x equals natural log of 4 minus 3x. Domain. Okay, so we have to remember the domain of a logarithmic function. So looking at the parent function, let me note that the domain of, just sort of our general y equals log base b of x is going to be 0 to infinity for all b, real numbers b that are greater than 0 and not equal to 1. Okay, so no matter what b is, log base b of x is going to have a domain from 0 to infinity. And you could just think of the parent functions, whatever. Here's log base 2 of x. I always just sort of remember the graph of a logarithmic parent function looks like that, where the graph is completely on the right side of the y-axis. Okay, so what that means, the implication of this is that the domain of y equals natural log of x is going to be 0 to infinity. What we have to account for is that on the inside of this function, we have this little linear expression, 4 minus 3x. Okay. So since the domain of the natural log of x is 0 to infinity, that means, so I'll say thus, whatever goes into this function, into the parent function, x has to be greater than 0, right? We're only allowed to put positive values into this function. So this is for y equals the natural log of x. So now let's focus on our actual function. So I'll say now f of x is equal to the natural log of 4 minus 3x. That whole quantity is going into this function. So since the whole input is 4 minus 3x, we just need that 4 minus 3x to be positive. It needs to be strictly greater than 0. So we're going to set 4 minus 3x strictly greater than 0, and we want to solve for x. So I'll say, and solve for x. Okay, how about I add 3x to both sides? And I can divide both sides by 3, and I get 4 over 3 is greater than x. So what this result is telling me is that in order for a value x to be in the domain of this function, it has to be less than, strictly less than 4/3. So generally, with domains, we want to write them in interval notation. So I'm going to say the domain of my function f is equal to all the values of x that are less than 4/3. I can write it like this: -infinity up to 4/3. And I'm going to put parentheses at 4/3 because we can't include 4/3, right? Because this was a strictly less than or strictly greater than at the beginning of the problem. Okay, and I want to give you a way that you could check your work for this problem. If we go to graph this, like you have a graphing calculator, if you graph this function on your graphing calculator, you can type it in because we actually have a natural log button on our calculator. You'll graph it, and you will get a graph that looks something like this. This is going to be a very rough sketch. But, you know, here's our x and y axes. We are going to have a logarithmic shape, which looks something kind of like this. Sorry, that was like a very, very crude. Something like this. You're going to see that there's a vertical asymptote right around here at the line x equals 4/3. Okay, so I don't know exactly, what the graph is going to look like, but you can look it up. And if you see something that appears like this, you can be a little more confident in your answer here because we were told that we're only allowed to plug x values in that are less than 4/3. So your graph should appear only to the left of that vertical line. Okay, so that's it for just sort of our initial review of logarithmic functions. Next, we're going to shift gears a little bit and we're going to talk about solving exponential equations. So exponential equations are equations which involve variables in the exponent's place, and we want to be able to solve for those variables and assign values to them. So here are a couple tools that are useful in solving exponential equations. Sometimes we'll want to rewrite the exponential equation in logarithmic form. Okay, so rewriting, going between those two different forms can be a useful tool. Common bases is another tool that we'll use. Sometimes we can rewrite an exponential equation in this type of form where we can have the bases matching. And this is really convenient because if we ever have 2 to the x is equal 2 to the y or something like that, the implication is that x is equal to y. All right, and this is true because exponential functions are 1-to-1. This is just a direct result of that. Okay, so common bases, I might write that. Common bases is something that we can use. And then if you have two different bases, like, here's an example, 3 to the x is equal to 2 to the y, you can take the natural logarithm of both sides of the equation. And that can give us a path to the solution. So let's do a few examples and I'll demonstrate each of these techniques. So for example 7, we have this equation. We want to solve for x. The equation is 2 to the x equals 4 to the x plus 1. So I'm going to tell you right away, common base is the easiest way to go. Because if we can take something and rewrite it with no variables in the exponent's place, life gets a lot easier. Then usually we're just solving, a linear equation or a quadratic equation if it's a more challenging one. So oftentimes when I'm looking at an exponential equation, I'm thinking, is it possible to write this in this form where I have just, b to the x equals b to the y? So here I don't have common bases right off the bat because, this is a base of 2, this is a base of 4. Obviously 2 and 4 are not the same number. But 4 I can rewrite with a base of 2. So check this out. I'm going to rewrite this 2 to the x. Left side is not going to change. But on the right side, I can rewrite 4 as 2 to the second. And this whole thing is still raised to the x plus 1. Okay, and then I have a property of exponents. If I have an exponent raised to another exponent, remember we have this property, if we have x to the m to the n, I don't think I used m's and n's earlier in this section, but this is how the property works. You multiply the exponent. So this is x to the m times n. Okay, so just a little reminder of that property, because that's what we're looking at right here. So I can rewrite this. Left side still is unchanged. Right side, I can write this as 2 to the 2 times x plus 1. And I could just multiply in the exponent's place up there and write this as 2 to the 2x plus 2, like that. And now, the great news is we have common bases. Okay, this is always great news. We have common bases of 2. So what I can do now is I can just drop those bases and just set the exponents equal to each other. So now I can rewrite this equation as just x is equal to 2x plus 2. Which is a very, very simple equation. This is a linear equation. We can solve this pretty quickly. I'll subtract 2x from both sides, and I'll have negative x is equal to positive 2. I can divide both sides by negative 1, and I get my answer, x is equal to negative 2. Okay, I would encourage you to check your work. And we could do this by just substituting x equals negative 2 into our original equation. It'll look like this, 2 to the negative 2. And we're hoping, I'll put a little question mark over this equal sign, we're hoping that this is equal to 4 to the negative 2 plus 1. Okay, so simplifying on the left side, this is just 1 over 2 squared. And this is, 4 to the negative first power, just simplifying. And this is 1/4 on this side, and this is 1/4 on the other side. So it works. Okay, so just to confirm that my answer is correct. It's especially important in this section that we check our answers because it is possible to get some extraneous solutions when solving exponential or logarithmic equations. So I'm always in the habit of checking my answers, even outside of this section, but it's especially important here. Let's look at example 8. We want to solve this equation. 5 to the x squared is equal to 625. Okay, so common bases, I always try to shoot for those. And 625, seeing that 25 on the end has me kind of a little bit alert here. Like, is that a power of 5? It turns out that it is. 625 is the same as 5 to the 4th power. Okay. I honestly did not have that memorized as like, a 4th power of 5, but I just sort of pulled out my calculator and started raising 5 to different powers to see if 625 was one of the numbers that appeared on the list, and fortunately it did. Okay, so now we have common bases. I can just rewrite this as x squared is equal to 4, right? Just setting those exponents equal to each other. We can do that whenever we get common bases like this. And we just want to solve this quadratic equation. There are different ways to do it. You could solve it by taking the square root of both sides, or, you could subtract 4 from both sides and solve by factoring, like this factors to x plus 2 times x minus 2. So I get the two solutions, x equals negative 2, x equals positive 2. So those are my two solutions. If you did solve by taking square roots, you would just get x equals plus or minus 2 when you took the square root. Same answer. Okay, you could check your work for that one. How about example 9? We want to solve the equation 10 to the x is equal to 50. Can we get common bases here? Is 50 some power of 10? No, unfortunately it is not. 10 to the first power is 10, 10 to the second power is 100, so we're not going to get lucky in that way this time. Let's try to take the logarithm of both sides and see if that helps us. So this is a common technique which bails us out in these sort of less friendly types of situations where we're solving exponential equations. What we can do is we can take the natural log both sides. So natural log of 10 to the x is equal to the natural log of 50 and the reason this is a helpful strategy is because we have this nice property of logarithms. So let me write this over here. We have this property of logs. If we ever have log base b of x to the n, where we have, the input of a logarithm raised to some exponent, we can bring that exponent out in front as a factor. So this is the same as n times log base b of x. Okay, and this is really why logarithms were sort of like defined and created and explored. We need to solve exponential equations in so many situations because, as I mentioned in the previous section, exponential functions model a lot of stuff in the real world. And we run into this situation oftentimes where we're trying to get, the variable out of the exponent's place. And logarithms, being an inverse to an exponential function, does just that. So here's what I can do. I can bring down, looking back to the problem at hand, I can bring this x out in front, and then I'll just have natural log of 10 and still just natural log of 50 on the other side. And now that x is out of the exponent's place, because it's like a big challenge when we have a variable in the exponent's place. How do we isolate that variable? This is how we do it. So I'm going to divide both sides of the equation by natural log of 10. So natural log of 50 over the natural log of 10. And now this is something that I can just type into my calculator because we have that natural log button on there. So I get that x is approximately equal to 1.69897. I'll just round it to 5 decimal places like that. And you can express your answer this way. You could have expressed your answer, given the exact exact solution like that. But that is how we would use taking the natural log and using that property of logarithms to solve an exponential equation like this. And we use natural log because we have a button for it on the calculator. We also could have used log base 10 because we do have a log button. There's a button that just says log or maybe log of x on your calculator. So you also could have taken the log base 10 of both sides of the equation instead of using the natural log. That would have worked out fine as well. But I just wanted to point out that's why we use natural log, is because we actually have a button for it on our calculator. We don't have a log base 2 button on our calculator, so we don't use that one. Page 33, compounding interest. So this is a business calculus class. So we want to know about how this number E is really, really helpful and widely applied in financial situations. Okay, and this is because of compounding interest. Now, generally speaking, what compounding interest is when you earn interest on interest. So a little side example, like let's say that you invest or you put into an account which accrues interest $100. So you start out with $100. And let's say that your interest rate, so your rate R, is 10%. Again, keeping it very simple. So it means that you get paid 10% every, year? Let's say annually your interest rate is 10. So the first year, like your initial value, your P sub 0, or your P, is 100. So after year 1, so like if T equals 1, then you're going to have $110. Right? And this is because from here to here, you earn 10%. And 10% of $100 is $10. So you got plus $10. Okay, now let's say one more year passes. So now we're at T equals 2. If this interest is compounding annually, how much money are you going to make in this second year? It turns out that you're going to make $11. Okay, and you're going to end up with $121 after 2 years. So the reason you get $11 added to your account balance this year instead of 10 is because the interest is calculated using this number, not the original number. Okay, so that $10 in interest that you earned in the first year, we also earn interest on that in the second year. So that's why we get $11, because this is 10% of this balance here. Okay, so this was a very, very simple and sort of quick and dirty example to show you how compounding works. In this case, we're talking about being compounded annually. Okay, for continuously compounded interest, it's not just once a year, it's happening constantly. You're constantly compounding that balance. Okay, so our formula is this. S, and that's just your account balance, is equal to P times E to the RT. And this is where P is the principal amount, the initial investment or the initial amount. T is the number of years, is usually what we're going to see in these types of applications, but that's your time value. And R, of course, is the interest rate. So let's see a little example here. Example 10, a person invests $7,000 at 5% interest compounded continuously. So whenever I see this compounded continuously, I know that I'm going to be using a base E exponential function. And the question is, how long will it take for their account balance to reach $12,000? So we will use this formula. S is equal to P times E to the RT. We just got to figure out, okay, what am I plugging in for all these values? Well, p, that's the initial value. Which in this application we could call the principal. Which is just the amount of money that we start with. In this case, it's $7,000. Okay, how about R? This is our interest rate. And we are just given this, it is 5%. But of course, that percent is like dividing by 100, so I'll write this as 0.05 to get it into decimal form, so that it's easier to do the math with it. T, this is unknown. This is our time value. And we're being asked for this. It says, how long will it take for their account to reach 12,000? And this is unknown in this case. All right, so T is what we will be looking for in this problem. And the last thing is S. S represents the final value. So after some time has passed and some interest is accrued and the account balance increases, the value we have for this in this problem is 12,000. Good, so what we should do here is plug in the values that we have, and we're going to be solving for t. So here's what I'll do. I want to plug into s is equal to p times e to the rt. So that'll be 12,000 is equal to 7,000 times e to the 0.05 t. Now I want to solve this exponential equation. A good first step is to get the exponential part by itself. So I'll start by dividing both sides by 7,000 just to isolate that e to the 0.05t. Okay, and I'll just simplify this fraction on the left. I could just write this as 12 over 7, canceling that common factor of 1,000. All right. And to solve this, so I am not going to be able to get common bases, right? I don't know a reasonable way to express 12/7 base e. So I'm going to use that approach where we take the natural logarithm of both sides. So we'll take the natural log of both sides of the equation. Here I have the natural log of 12 over 7. I'll just leave it like that for now. And remember, taking the natural log is helpful because we can bring down that exponent. So I'll bring down 0.05t as a factor out in front, and then I'll have the natural log of e left over. And I can simplify this. What is the natural log of e? Remember, this is just asking e to what power equals e. That's just going to be 1. Okay, whenever we see natural log of e, this is a nice thing to run into because it just equals 1. Just draw a big 1 around that. So that'll go away. Whoops, 0.05. And I'm very close. I just have to divide both sides by 0.05. So the natural log of 12 over 7 divided by 0.05 is equal to t. Now, given the nature of this application here, I think I want to just represent this in decimal form. So I could plug this into my calculator. I did so very carefully, and I got 10.78, just rounding to the nearest hundredth there, is equal to t. Okay, and remember, t is measured in this problem in terms of years. So to answer the question, because the question was, how long will it take for the account balance to reach $12,000? So I'll just say the balance will reach $12,000 in approximately 10.78 years. And I'll box that up. All right, and that brings us to the very end of chapter 1, which is our sort of quick and dirty review of a lot of the stuff that we learned back in college algebra, or maybe back in algebra 2, or your algebra in your high school classes. And just to get the sort of basic skills that we need to be successful as we move into the actual calculus, which we finally get to do. In chapter 2, we're going to start talking about limits, and then we'll move into derivatives and a whole bunch of really interesting and useful applications. So I will see you in the next video at the start of chapter 2.